Okay, let's get started. So I'm kind of sorry that I couldn't make this video earlier. Well, I had to take care of a lot of stuff and there's grading and all of those. So yeah, but I am making this one for Friday. So yay, finally some videos to watch, right? So one little thing about this whole lecture is, okay, I don't know if it's going to diminish your motivation of watching this video, but yeah, this is not going to be in the exam. Yep, I said that. But it's going to be helpful for you in binary bomb because from what I heard, there is going to be a phase with linked list in binary bomb. So it's best if you understand what we are doing here. And what else? Yeah, we are going back to C again. So that's a good news or bad, like however you want to see it. And what else? Hmm. Yeah. Okay, so one small thing. So if you look at the bottom of the slide, you can see that we are using a very old version of the slide. So there was a new version, and the main reason why I didn't make the video was because the new version is super complicated and I really wasn't feeling like explaining it. So I talked to John and we decided that we are going to use the older version just because it's much easier to understand and it's much easier to explain actually, and it gives you enough idea of everything that's happening. The newer version is super complicated and honestly you really don't want to go through that. Trust me, trust me on this. So yeah, let's get started, and I hope this video is going to be smaller than usual or not, I don't know. So yeah, linked list is something like a chain of memories linked together. So you may ask, like, why are we not just using array or something like that? Okay, so not always you are going to be using array. Sometimes you just want to chain together a few memories which can be anywhere in the heap, and that's when the linked list actually comes into play. Like it connects together a lot of different data structures. Like, okay, so it's a generic linked list, so it doesn't necessarily has to be of the same data type. Like for example, if you make a array of an integer, every single thing in that integer is going to be, well, array is going to be an integer, right? You cannot just like put a double over here and you expect it to work correctly, because it will just like cut off the floating point part. So yeah, the thing we're going to take a look at is a generic linked list, so it can actually take care of any sort of data type, which is pretty cool. This is what a composition of a linked list may look like. We will be having a head, we will be having a tail, and everything, like every data is going to be within those two. Okay, so this is a different approach to a linked list. Usually the linked list is kind of like this, like it starts from a head and it just like connects bunch of memory nodes and stuff, and it ends in a null. So the usual check is, if it's a null, then we know that we came to the last part of the linked list. So that's how we do iteration. But in this case, we have a head and we have a tail. We use this to find whether we have found our beginning or ending or anything like that. It takes care of the whole null thing, so you are saved from null pointer exception and all of those. It makes life easier, maybe a little bit complicated but still easier. So yeah, the structural consideration, like what we consider while making the linked list. The use of guard nodes at the front and rear of a linked list eliminates the special cases when implementing insertion deletion options. That's one of the special cases, is the one I just like mentioned, being null. And there are other cases like you may lose track of the head, you may lose track of the tail, and you can actually put data in the head, which is also complicated, and sometimes you want to add a data on the head. In that case, you have to change the pointers accordingly. So yeah, there's a lot of cases that makes it complicated, but using front guard and rear guard actually makes it much simpler. This way, every data node will lie within the two nodes. Like this is the starting point, this is the ending point, and everything will be within this part. Like you cannot go beyond that. The common alternative is to simply have pointers to the first and last data nodes, probably stored in a list object. That leads to a special case when operating at the front or rear of the list, like I mentioned. So these are the stuff you need to have in a linked list in general, like initialization function to set up basic structure of an empty list. We know that we need to initialize everything. It should be able to insert stuff, insert functions to add new elements to the list, at front, at rear, at user selected position, or ordered insertion. Ordered insertion is basically like sorted way of inserting thing. Okay. Remove function to remove elements from the list. Find function to determine whether a given element occurs in a list. Clear function to restore the list to an empty state, like free everything that you had. In C, we would organize this as a part of struct types, list and node, and collection of associated functions. Okay. So every single thing that like every single the whole sorry, my bad. So whole implementation is actually given to you in the course website. If you go to the course website and check the code examples tab, over here the implementation is given to you. Let me take a look at it when you have time, and if you don't have time, don't bother. But it's pretty cool. Like you'll have a bit hard time to navigate through it, but like after this lecture you will understand like what's happening and not, and so on. Okay. So yeah, every single implementation of every function you'll be seeing are given there, so take a look at it. Okay. So this is the beginning. This is how our structure is going to look like. We are going to have a node object and we're going to have a list object. The node object is going to have a pointer to previous and next. So if this is our node, it's going to have a pointer to previous and a pointer to next, which points to another node type. Okay. And we have a D list which has a head and tail, like you have seen the rear guard and front guard. Okay, we are doing type def here. You can do it in one line if you want. I usually prefer doing it in one line, but this is the usual convention. Okay, so this is what the initialization looks like. We have a denote head and denote tail, as you have seen over here. Head is a type of denote, tail is a type of denote, and this belongs in a object of dlist. So the whole object is dlist. It has two denote head and denote tail, and you know that denote has a denote pointer previous and denote pointer next. So same for tail. At the initialization, the previous is going to point to null, like it doesn't have a previous, right? So it's just going to point to null, but the next is going to point to the tail. Same goes for tail. Tail's previous is the head, but it doesn't point to anything, and it's a null. Oh my god, I'm very sorry about my writing. Anyway, this elements the special cases because every data node will always be between two other nodes. We could also make head previous point to tail and tail next point to head, which would eliminate null pointers and allow the list to be used as a circular fashion. You can do that. You can not do that. It's up to you, because like if you point it here and you point it there, it's a circular list. Okay. So another thing we're going to do is we're going to use something called duct tape, and this is how we are going to like duct tape objects together. So instead of having something like a array or like a linked list like Java, we are just going to use something of a duct tape. Yeah, that name is super weird, but like I don't know. That's what we have decided to call it. We may use a single dlist of denote objects with any user data type without sacrificing typecasting. Okay, we merely have to create a duct tape object to attach a data object to a node. So this is what our structure is going to look like. We are going to call it integer dt. It can be a float dt, and inside there, instead of int, you can put a float or anything you want. And it also has the denote. Okay, so we know that the denote has a previous and next, right? So this is how we are going to connect it with the head and tail, and we are going to put our data over here in payload. Okay, so this is the usual typecasting, and we have a initialization function where we send a object of integer dt, and we also send the payload we want to put inside. Okay, so this is the usual structure that's going to look like for the list. So we have our dlist. It has head and tail. We know that everything is going to be within head and tail. So head points to a integer dt. Well, it doesn't directly point to integer dt itself. It actually points to the node that's inside the integer dt, and they are connected with each other with next and prev, and their payload is inside the integer dt. Okay, so this is how they are connected. So in this case, dlist only knows about two denote objects, which are head and tail. Each denote object only knows about one or two other denote objects, because in this case head only points to the next, right? But it doesn't have anything on prev. And in case of tail, tail only has a prev and it doesn't have any next. And this one has a previous which points to head, and a next which points to over here. Okay, the dlist and denote object know nothing about integer dt objects because they are connected with node and not the integer dt itself. Okay, so when we want to connect, like we want to add or insert a node inside the dlist, well, this is what we do. Okay, so the first thing we do is we are going to take this next of the new one. We're going to point it to the old position, and then that old position is going to point to our new node. Okay, and then our new node is also going to point our previous with the this part, and its next is going to be replacing this with this. Okay, that was a terrible explanation. I'm trying my best here. So let's take a look at the code to make it more understandable. So elim prev, this is the elim, right? Its previous is going to point to before prev. So this is our prev. This is just a node. Okay, so this prev is going to point to its prev. So it's going to start pointing over here. Then in the second line, we have elim next equals before. So next is going to start pointing over here. Then we have before, previous, next. Okay, so before, and that's previous, which is here. And then its next is going to point over here. And then before previous equals elim. So then we have before previous ln. Okay, did that make sense? It's a mess, but like I think it's pretty straightforward. I think you understood what I'm trying to like explain here, right? Please say yes. So anyway, this is how our code is going to look like, and there's the usual error checking that we are checking whether before is actually inside there. Is it the tail or not? If the element we have sent as a parameter actually valid object or not, and then we are using our code to do the insertion. The insertion itself is pretty easy. So yeah, then comes the searching part. So we know that they are connected with node, but we do not actually have access to the integer dt object itself. How are we going to like access that, right? Because we know that if you go down the list, you are only accessing these nodes, but you don't know the payload that's with it, because you are accessing this data, not the whole data, right? So how are you going to do that? We are going to use something that like some shenanigans we use in C. So let's see what we're going to do. So if you remember the whole assembly thing, it's going to come in handy. So we have a integer dt object, right? So integer dt has a payload and a dnode, and the dnode has previous and next, right? So p is actually pointing here. Like let's assume we have a integer dt and this is the node. So p is actually pointing here. Like when you go down the d list, p is going to point to the nodes, right? So it points here, but we want to go to this integer dt. How do we do that? We just skip the payload and start pointing here. So this is the starting point of integer dt, right? So usually, like in this case, if payload is an integer, we can just do -4 or something like that. But what if you're using a double type? Or what if it was a character type? If it was a character type, it should be just -1. If it's a double type, it should be -8. So how do we make it dynamic? So to make it dynamic, we have another function, which is offset off. Okay, so it's a standard library. The standard library includes a relevant C macro, offset off. It takes two parameters. The first one is the type, and the second one is where the member is. It expands to an integer constant expression that has type size t, the value of which is offset in bytes to the structure member designed by member designator from the beginning of its structure designated by type. Okay, that's a very complicated sentence. So to make it simple, the main idea is we use the offset function. Actually, it's a macro. It's not a function. We'll see the difference between macro and function, or maybe not. I'll just try to explain it when I can. So yeah, in offset, we are going to send the type, in this case, f, because this structure is called f. And we are going to send a member. So in this case, the member 3. This is what we're sending. So then it's going to return us how to go back to the top of it. So it does some -4, -8 or something like that and gives us this location, the one we were looking for, right? So if we have access to the member, which is in this case the node, we can actually get the address of integer dt. So to do that, we basically do something like p, which is the node, minus offset integer dt, because that's the type, and the node itself, right? It would almost work, but there is a little bit of little bit of typecasting you need to do, because it needs to be a pointer arithmetic so that it works for everyone. So then you introduce the type over here. Okay, because if we go back, we saw what Hmm. Well, the reason in this case it's uint 8 because our p is the size of 8 bits. Hmm. Because it's a very older version, so we are using a address of that like uint 8, but like if you are using a very newer version it will be something like uint 64t. But like I said, we are using very old slides, right? So that's why it's uint 8. Okay, so we do a typecasting for p, and then we minus the offset, then we typecast it to integer dt. So then we will be having the address of integer dt by doing this, right? We can actually make a macro for that. Okay, so the idea of macro in C is kind of like lambda function in Python or Java. Yeah, the newest version of Java has lambda functions. So it's like, or like inline functions. Okay, so they are just like one line. You just define them in one line and they work just like that. So we can do something like this. So far we have done something like define pi 3.1416 or something like that, where pi's value cannot be changed, right? So we can do something like this for making macros. Macros are just like one line function, if you want to call it that. You can also write macros for loop, which I kind of forgot how it looks like. Like if you write something like for I 1, and then you write the rest of the part. Sorry, this is the range. Then you don't have to write the whole thing, and instead you can just write this part to replace it. Okay, so that's how macro works. And honestly, if you ever go through any C projects, like big C projects, you will be seeing a lot of macros. Okay, so that's why I just wanted to give you a very basic idea of macros. So they are like inline functions. They just like replace their like what's written there with what they are supposed to be replaced with. Like for example, if we write something like dlist entry node struct member, it's like parameters. They are just like replaced with this part. Okay, and by using this you can actually get the address of int dt, which we were looking forward to. So this is just an example of how it works. So I already explained it, so I think you should understand what it's doing here, right? Like I said, the preprocessor sees code whose pattern matches in the macro interface. It replaces the code with code generated from the macro body, like I said, right? Yeah, if you don't understand, don't worry about it, because you probably won't be needing to use macro in your life. But like, if you want to call yourself a C programmer, this is a concept you should know about. Okay, so here's a function to traverse the list, and apparently this list has a bug in it. Like, wow, I am sometimes surprised with the humors in these slides. Yeah, I don't make these slides anyway. So yeah, this seems pretty simple. We are just going to go down the list and then check whether it's at the end of it or not, and then we can get our data like pdt by using dlist and do whatever we want with it. We can also put our user data, get our user data from the payload and stuff. So yeah, it seems pretty straightforward, and we will see how to debug this code in the next class, which will be a gdb and linked list, and to see how the whole thing works. And that class is going to be pretty intensive, but yeah, it will be fun. So here are other functions that you need to implement, like for example int, the initialization, the insertion, remove, whether it's empty or not, and how to clear it. The implementation is given in the course website. You already seen that. So yeah, if you're interested, you can take a look at it. There are also some helper functions you could have used, or like macros, like for example, dlist beginning, dlist end, dlist next, previous, head, tail, something like that, so that you have more power over the dlist. There's also push and push front and push back. It's kind of like stack or queue. Like you can actually turn it into a stack or queue by implementing these functions. But yeah, so that's it for this video. I hope it kind of give you an idea of how generic lists are done in C. And yeah, I'll see you in the next class.